Okay, so it's a 2 hour. So in the first hour, I will do on the whiteboard. Okay, so it's it's a synthesis of joint work with plenty of people, and as the title indicates, is related to the uniform estimate on particle type filters. But first, to better introduce this subject, I think it's better to show you when you have a nonlinear equation, how to do the particle approximation, how the particle approximation is a perturbation of a nonlinear equation, and you need to study the stability of this to get uniform estimates. So I will just show you the general principle and how it works, discrete time and continuous time. So the first, let's say in discrete time, so I will not restart the notation of the other day. I think everyone I think they are fixed now. Apart Daniel, you use P eta instead of eta P, but it's okay. So discrete time. So I suppose I have, so let's say S is a state space. And I'm taking eta, that's the probability measure on S, some probability measure. I start at some probability measure. And I look at this type of system, which is simply a function of the previous one, starting at 0. So phi, it's simply an application from the set of probability measure in the set of probability measure. And just to give an example, oops, not this one. Eta t, eta n on some measure. If I look at some function, maybe this one, eta, some function that may depend on the time, some Markov transition, and I divide by eta gn. So here, so this is an example, and I take gn positive, let's say less than 1, and mn x dy is a Markov transition on S. Okay, so that's an example. So suppose you are given a system like that, you go from a probability measure to another probability measure, and then you can always find, so then you can always find some Markov transition that may depend on n and eta, Markov, such that eta n is eta n minus 1 and the Markov transition. So basically, you can rewrite this in the following form, always. If this is the case, so an example, this is not unique, but an example will be just take this, and it works. It doesn't depend on the starting point. Another example related to this one, you can check it works. In this case, is k n eta x dy is gx mx dy plus 1 minus gx and eta g and m and f. Maybe I just, yeah, it's fine. Eta g. No, it's not well defined here. So I should rewrite this in another way. Example, I take this one, acting on some function at x is 1 minus gx mf of x plus 1 minus gx and eta g mf by eta gn. So you can check that this works. It's a Markov transition because if you take f positive, this is positive. If you take f equal to 1, you can check it's equal to 1. So it's a Markov transition. is the chance to go. That's the mean of a transition starting from of a function of the new state, given you start at x. Okay? So as soon as you have something like that, instantly you create the n, so the mean field particle model, which is quite simple. It's a particle system that lives in the same space as this, but in the product space. You start with, let me call this psi n. So you start with IID copies with the same law eta naught, just to approximate the initial condition. And as soon as you have this, then you sample the chain from this to this, just sampling the transition, where you replace the true law. Yeah, you replace the true law by the empirical law. Okay, so you just do that. Yeah.
One of the in your example is GX, right? What you find 1 minus GX.
Ah, yes, thanks. Thanks a lot. It's GX. Thank you. Okay, so if I do that, for example, you see there is just capital N here, capital N, because this is the law of the, this is a Markov transition. So if this is the law of the state at time n minus 1, this will be the law of the state at time n, because this is the chance to go from n minus 1 to n. So it's simply a simple formula. So this is a Markov transition, but it depends on the law of the system. So as soon as you need it, you replace by this. So if you do that here, it doesn't change much. But here what you have is for each time you are somewhere, with this probability, you evolve. Of course, I forgot all the indexes here. But with this probability, you evolve with a Markov transition. And with this probability, if you look at this measure, it's simply sum over n, gn or psi I n minus 1 by the sum m n f psi I n minus 1. So with this probability, you explore. With this probability, you don't feel well, so you change your location. You select a better location with these weights. And from there, you move to explore the space. Okay? So it's just a direct application of this general principle. Right? So now, as soon as you have this type of trick, which means that as soon as you have something like that, you apply this trick. And then the next step is to say, okay, locally, square root of n, the empirical measure at time n, if I compare to the true, eta n minus 1, you look at these guys. This is the mean of this given the past. This is the mean of this given the past. Okay? So if you can rewrite, you are sampling each guy starting from this guy according to this transition. So there is a CLT on this one. It's a local CLT, simple, more or less. If you want to see it more clearly, in the example, in this one, so let's say this is the example, the blue one, the example 2. So you destroy this and you have only this. In the example 2 is only this. So that means that in this example, you are sampling IID, so conditional IID, according to the transformation of the empirical measure. So in the second example, you don't even care where is this guy, because the transition only depends on the function of this one. So you don't care about this. And these guys are sampled according to this law. So there are IID according to this, given this, of course. So here is simply empirical measure, IIDs with this law. So it's the law of large number, the CLT, that tells you that this guy, if you call it like that, this guy converges to some centered Gaussian random field. Or if you prefer, if you take one function, you look at the empirical value of the function compared to the mean given the past, you get another error, function by function, and this converges to some Gaussian with a given, is centered with a given variance you can compute. But the funny thing is that you can rewrite here and you obtain this formula that tells you that you solve the system plus an error. So it's really the same. I'm just rewriting this in that form. So this is totally equivalent. But this tells you that you are really solving a system we had before. We are making this perturbation, and these guys are almost Gaussian random fields. So they are centered. The mean is 0. And if you look at test functions which are norm less than 1, the variance of this on some function will be less than 1. Okay, so that's the way to see that if you do a particle approximation like that, this one, or you start from this, you create this is a Markov chain. You obtain this type of object, which tells you that what you are doing mathematically, you are perturbating a nonlinear system. So this has to be thought as a perturbation, let's say stochastic perturbation of a nonlinear process. Okay, so that's the way to look at this. And then there are many ways to analyze this problem, but you know, everyone knows in numerical analysis, if the nonlinear system is stable, in some sense, when you do some perturbation, this local error will not propagate. Okay, so there are some principles to analyze this trick. But the main idea is to look at the particle approximation as a perturbation of a nonlinear equation. Okay, so this is in discrete time. That's the trick. Okay, so now let's do in continuous time. So continuous time. So the same notation as before, R, S, some state space, P of, so I consider a flow of probability measure on S, and they evolve, and L, it, maybe I need to do some brief reminder on generators. I will do something different. So let's start with some process which evolves like that. dxt, bt, xt, dt, plus sigma t, eta t, xt, some Brownian motion. You can think in multidimension or not multidimensional, as you want. You can suppose that there are, so this is between jumps. Let's say I create jump rates lambda t, eta t of xt. And when it jumps, when the jump occurs, you go from xt minus to xt, choosing this one according to some transition, I don't know, m, that may depend on t, eta t, xt minus dx. So you see how it works? The jump rate, so what is this? That's the law of the process xt. It may depend on the law of the process xt. So there are conditions. So you see you have a diffusion. As before, the transition, if you make the discretization, as Cody did previously, if you write the discrete time version, you go from this state to this state. You can think of this state as being xt plus dt minus xt. So if you are in xt, you need to compute the law of xt, and you need to do this operation, to go to the next. And you continue like that. You have some jump rate, which everyone knows the jump rate. You wait some time, and when this time, so the jump rate tells you that you wait the first time, this goes above some exponential random variable with parameter 1. So you sample an exponential random variable with parameter 1. At time 0, this is 0. And then the time increase. This is positive, is the rate. So this quantity increase. And when it's above your exponential, you have just sample, then you jump. When you jump from where you were, let's say here, there is a hole, you jump to a location randomly chosen according to some Markov transition, which may depend on the time and the law of the process. Okay? So that's the abstract and general definition of a nonlinear process in continuous time. Yeah? Yes?
Is there a name for this type of process?
There is a name for the evolution of the law, which are integral differential partial equation in the space measure value processes. Or this one is called nonlinear Markov processes. Maybe I can give an example. If you don't have the jump rates, you have only this. These are called, so without jumps, it's called Markin-Vlasov process, diffusion. When you have the jumps like that, there may be plenty of things inside. You can have the Boltzmann equation when the shock makes the jump of the velocities. There are plenty of equations which fit into that. I think Sylvie Méliard made a paper, I think in 92. I don't remember. I can give you the references, where she studied general models like that, including the jump, so that to represent the Boltzmann equation, the Moran model, the Nambu systems, and plenty of examples. So it's a general framework. So I would say nonlinear Markov processes. And the most famous one is the Markin-Vlasov diffusion, for which you have only this part. For ensemble Kalman filters, you will have a dependency on the diffusion part. But typically, in fluid mechanics, this doesn't depend on nor in the state nor in eta t. The dependency is on this point, on this state. So an example of this, a typical example of this drift will be you integrate with respect to eta some function, let's call it like that, don't know, or let's call it b again, y and x. That's an example. Typical example people are using. Okay, so if you have this type of model, it's a nonlinear process. And the generator is quite easy to write it. If you look at the evolution of the law of these guys, so eta t is the law of xt. You take a test function, which has to be at least twice differentiable because you have the Brownian motion. And you look at the evolution in time of eta t of f, which is the integral of f with respect to eta t. I take fc2. Then you obtain an equation like that. Oops. This depends on the time, and eta t, and f. And L t eta at x is what? Is b eta x, first derivative, 1/2 sigma 2 eta x, second derivative, so xx, and you have the jump, so lambda t eta x, f of y minus f of x, and mt, so it's pretty long, x dy. Okay, so that's the way. In fact, usually we don't even write this. Typically, you just write the generator. This is the drift, which corresponds to the deterministic exploration. That's the second term coming from the noise, the Brownian motion. And this tells you that at that rate, you jump from x to y, choosing y according to this Markov transition. And there are plenty of ways to rewrite things, but that's the one way. So this corresponds, remember in discrete time when we wrote this, it looks like that, how you go from one to the next. Here is more messy because you need to apply Ito formula and play with this stuff. Okay? But it's basically the same equation. Right? So when you see something like that, instantly you see drift, diffusion term, jump term. Right? Let me call this process, as I call it x here. If you take any function of the process, you will have the generator. It has to be C2 again, plus a martingale. So I'm sorry because I'm using again the same. So let me call it K here to change, to distinguish with the martingale stuff. Yeah. So if you take any function of the process, you obtain the evolution of this is given by the generator plus some martingale. And of course, if you take the expectation of that, the martingale disappear. The martingale will disappear, and you will have the mean of this. And the mean of this means you integrate that point. So it's the mean of this with respect to this law. So it's exactly this formula. Okay? So this formula implies this one. Right? As usual, when you have a martingale, you know that in the average is 0. But if you take the square of the martingale, it's no more a martingale. Okay? So M, the martingale, if you take the square, is no more a martingale, but what we call the angle bracket of the martingale is some process such that this is again a martingale. Okay, so this is called the angle bracket. An example, if you have something, I don't know, g of xs dws from 0 to t, of course, this is a martingale for some not normal diffusion and so on. When you take the square, it's not more a martingale, but if you subtract the integral of the g square, it's a martingale again. So the angle bracket will be related to that. So I will not talk about this. Okay, so in that situation, the key point is that this can be computed using what is called the carré du champ here, Ls eta s, ff, xs ds. So there is a generic way, I will define what is the carré du champ. There is a generic way to study the amplitude of the martingale, how big it is. In the average, 0. But if you take the square, it's not 0. So if you take the mean of this, it will be the mean of this. And the mean of this is given by this. So if you can control this term, then you control the variance of the martingale around 0. So this is very important. So the carré du champ of any generator, let's say f and g, because this is true if I take the martingale with f, the martingale with g, and multiply, I have the carré du champ with mf and mg. Well, so let's do it for only one. It's quite simple. It's L of f squared minus 2f LF. So that's one trick. So if I give you a nonlinear process, where I give you a generator like that, which is nonlinear, you know that if you take a function of the process, you will have this property all the time. So it's the Ito formula for the general type of models. So you can see this as the Ito formula. For any type of process, even nonlinear, you don't care, it will be the same. Okay? It works for jump, it works for any type of process. So that's why I think it's very important to keep this in mind. Sorry? If it's a local Martingale, I'm not talking about these details. Yeah, it's a local Martingale. I need to have this guy to be Lipschitz. I have plenty of conditions, otherwise I cannot even say that this process exists. Yeah? I assume everything exists. Yeah. Yes, this is the predictable part, and this is the Martingale part. But it comes from the Ito formula. You have no choice. The same. Okay, so keep in mind this trick. If you have the generator, and you write for any function of the process, you will have a Martingale, and you know how to measure the amplitude of the Martingale around 0 by the Carré-Duchamp. If I can prove that this is epsilon something, that means that the Martingale is very small, and the system is very close to this one, and so on and so on. Okay? So this is, I'm obliged to erase this stuff, but keep in mind this trick.
Sorry, what's the trick?
The trick?
Okay, so
I give you a generator. You take any function of the process. You can write with the generator and a Martingale, and you can compute the amplitude of the Martingale according to a Carré-Duchamp operator, which is defined in terms of the generator. Next step? No, just keep in mind this. I'm going to do the particle model for that. Okay? So all of this correspond to that only. So now I need to introduce the particle model associated to this. Maybe some point to say is that, for example, if sigma is 0, you have exactly the PDMP process, totally deterministic. It can even be nonlinear, you don't care. There is a rate. When you jump, you jump. Okay, it contains plenty of things. Basically, all the processes which may be nonlinear with respect to their dependency with respect to their law. Okay, it's a pretty general model. So there is a trick. If I give you something like that, you can say, what is the system of particle? System of particle is always the same. Intuitively, of course, you sample plenty of them. And when you need it, you put the empirical measure. And this is the empirical measure of the particles. Okay? Simple. Okay? So when you have this, there is a generator associated to that. The generator associated to the whole system of particles can be written in terms of the generator associated to this one. So I will write it now. So the generator associated to the particle system, which is defined as before, I will keep with this notation to avoid confusion. So it's a Markov process with some generator. So if I write a generator like that, you will recognize drift, diffusion, jump. This one has a generator which may depend on time, acting on some functions which are in the product space. I need to define a generator and function on the product space. And it's simply the sum, I to n. The generator I had before acting on the ith component only. So for example, if you have the derivative of with respect to the second and you derive the first, is 0. Okay? Only acting on the first. It depends on the time. It depends on the empirical measure you had at that time. And you act on functions where you fix these guys. You act on this one. And you take the value at xi. So that's the way to write one generator in terms of the other one. Pretty general. This says that independently, you have plenty of more or less independent particles, not exactly independent because this is here. But let's say more or less independent moves. Each particle has this generator. So if I put mx and I take at z to avoid confusion, let's say this is the derivative, second derivative, z. I put here the empirical measure. So it means that the guys are evolving as usual, but now instead of this, they will have the empirical measure everywhere. Everywhere. And when you will perform a jump, or when you will compute the drift, or when you will compute the diffusion, you will consider the one associated with the empirical measure at that time. Okay? So that's the only trick. This tells you that the generator is instantaneous differential velocity, let's say. So the particle evolve in some way such that instead of the true law, you replace by the empirical law. You can check if you take these guys with independent Brownian motion, look at the generators, you will end up with this stuff. Exactly this. So the drift depending on the current occupation measure, the diffusion depending on the current occupation measure, and so on and so on and so on. Okay, so you can define plenty of processes like that. So now, this is true for any function. So if you take the function of the process, of course you will have the generator acting on the function, xi t dt, plus a complicated martingale, which I know the angle bracket, blah, 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 and so on. Okay? The angle bracket of this martingale will be integral from 0 to t, the carré du champ associated to this guy, ls ff xi s ds. So I know the angle bracket, I can write this equation, and it's done. The same as before, exactly the same. This or this is exactly the same. For any process, it's like that. Take the generator, the martingale, angle bracket, defined in terms of the carré du champ, associated to the generator you are working with. So you just plug exactly this principle, Ito formula. So now, in fact, we are not interested of any type of functions. We like empirical functions. So what is an empirical function? How an empirical function evolves? So this is next step. So again, you can apply this to ensemble Kalman tricks, PDMP, and everything. It's a general principle. So now let's look at the functions of x1, xn, which are empirical functions. These are particular functions, very particular functions, because if you look at all the system, you don't have more than this. For this, if I just apply this, this becomes, if I do that, f of xi t will become eta nt of f. That means the sample mean of my function of the particles, right? That's my function, evaluated anxiety. So now you just replace the function and you just take the definition. It works like algebra, bam, 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 and you obtain the evolution of these quantities, which are exactly this one, is the same equation I had before. So that's fine, because this, I know, is the evolution of the true law of the system. And if it was like that, it would be finished. Because this is the evolution, I write it here. The evolution of the true system is like that. Okay, so eta t, the law of my process, satisfies this equation. Here I have something which depends on the empirical measure. So it's the first part comes from here. So this part is exactly this one. When you, instead of any function, you take empirical type functions. You obtain this. So that tells you that already you have a nice similarity. But now we have this guy. And now, again, you make the calculation, and you obtain something which is 1 square root of n. So Martingale, so I write it with a little m, so this is a little, this is a calligraphic one. This is a Martingale, and the angle bracket is simply given by 0t. Eta ns gamma L eta L s eta ns, my function ds. Okay, so that's it. So here what you have the empirical measure. That's the carré du champ of the generator I have defined previously on that location. It doesn't depend on the number of samples, apart that you have empirical measures. So when you apply this to some function, let's say that's more or less a constant. If the function is C2, bounded, this is a constant. You control this. It cannot grow more than t. Constant times t. Okay? And here you recognize this, which is the rate at the Monte Carlo approximation. So this corresponds to the formula we wrote previously. So this is this term is equal to this. And this corresponds to the formula we wrote, what was saying eta nn was psi n eta n minus 1 plus 1 over square root of n vnn. You remember we wrote this? Exactly the same. In continuous time, the analog of this is this formula. That tells you that you satisfy the same equation up to some perturbation, and you need to play with that. The same for this. So again, the stability of the limiting system is important to guarantee, in some sense, the uniform control of the local perturbation you are doing at each time. So it's the same ideas, again, propagating like that. Okay? So that's the principle. Okay. So now I think I can start the talk. I have how many minutes? 20? Chairman?
Break time.
Break time? No. 5 minutes? 3:40? Okay. On this will be nice if I have question on that, because I can switch then to the other one. Yeah. Oh, that's the idea. That's the idea. To have to analyze the stability of this guy, to enter the stability of the limiting system to analyze this stuff, it's always the same trick. Maybe I can do it now. Let's do it here. It's backward propagation, more or less. Backward propagation of errors. You do like that. You say, let's suppose I do no error in the beginning. I'm talking about the discrete time. Okay? Only the discrete time here. Okay? So suppose you start at time 0, and then you propagate at time 1, and you get eta 1, and you continue like that, and you make no error up to the end.
Yeah, can I just ask you a question?
Yep.
Now, you know what the form of phi n is?
Yeah, what?
Why don't you just substitute the empirical, to substitute the same decomposition in phi n for eta n minus 1. And then you have sum of errors plus high order terms. Then you
This is more or less the same, yeah. You mean you continue back in time like that up to the end?
then you have sum of errors plus high order terms. And
Yeah.
no disturbance.
Yeah, yeah, you can do that.
Because then you also have the Vn also.
Yeah. So that's one way to say yes. Let's do it as Sumit said. If you have this is a function. Eta n minus 1 is phi n minus 1 of eta n minus 2 plus 1 square root of n Vn n minus 1. I iterate. This is what you want to say? So if I have this, in fact, this, let's say, is the true one, almost, and this is my error. So I need to make a development on that. So this will be more or less phi n composition with phi n minus 1, this and this, eta n minus 2, plus 1 error, let's call it like that, because it depends on the first derivative of this guy, then we call it like that, plus this one. But I don't want to enter in the derivative of these flows. But if I do a Taylor expansion here, I can come back like that up to time 0. And I have an accumulation of error, and I can study how they propagate or not. But the picture, which is always the same, is that if you define the semigroup phi Pn, P less than n, as the way you go from P to n, that's the way you go from P to n, then starting from 0, if you make no error, you arrive here. But instead of that, because we make an error at the very first time, we make an error because we arrive here. And this guy, the only error we do is 1 square root of n, let's say. So 1 square root of n, some almost Gaussian field. That's the error between the two. Empirical, the true. We make one error. But if you continue without making errors, you will transform this guy into this. And of course, this one is not the same, because we make an error in the beginning. But if you wait a long time, this will be closed. So this is 0n, eta n0. So you make an error, right? This one is eta n0. And you iterate. Instead of doing this, we do that, and then we sample from that. So we make another error here. The error is eta n1 is exactly this one. Instead of the transformation, I take the empirical. So I pay this each time. So you make, again, the same error, square root of n, Vn1. And if you continue, you arrive to somewhere. So the true flow is doing that. The true flow is going here. And you need to study the difference between these two is the sum of the error you have at each step, like that. Is the sum of these errors. Okay, so in fact, typically you have the sum. So this error will be a sum of the way you forget. Let's say you forget with exponential minus lambda the time. So this is minus lambda n minus 1 and so on. So you will have lambda p from 1 to n. And the local errors you are doing at each step, let's say they pop out outside. And this is a constant, basically. Okay, so that's the idea. Said in another word, if you look at this, and instead of this guy here, you plug the solution, the approximated flow from 0 to p, starting from, let's say, eta naught. So let's say this is the approximation by sampling. You sample. This, in fact, is an interpolating path. So this is an interpolating path between, at time p equal to 0, you get this one, and at time p equal to n, you get this one. So this, how it changes in p, is exactly this, the variation in p. Because the value at p, the value at n minus the value at 0 is the sum of the differences. And the differences are these guys. So it's an interpolating path. We can do the same in continuous time. You write time s, time t, time 0, time s, and you need to compute the derivatives. Because when you look at the evolution in time of this, discrete time is another story, but in continuous time, you need to make the derivative in time here. So this one is okay. And the derivative in time here. So you need to study the gradients of these guys and how they change in time. So it's a bit messy to write. So in continuous time, we did that with Arnaudon recently in the archive stuff of in the 80s, in continuous time. The backward analysis like that, in continuous time, for the Feldman-Kac model. And in fact, if you look at all the analysis I'm doing on the ensemble Kalman filter and so on, always the same trick. To find a good interpolating path, because it encapsulates the stability of the limiting semigroup. And you can use it, if any. If they are not, then you get in trouble. Okay, so the same idea continues for discrete time. Make a break?
Yes. Thank you.
Thank you.